In Chapter 3c, we are going to combine the first and the second laws and derive 4 equations regarding the differential of internal energy, enthalpy, Gibbs energy, and Helmholtz energy, and their corresponding Maxwell relations. And then we'll see how Gibbs energy change when temperature pressure change. This will lay the foundation for the next few chapters. These are the 4 equations we are going to study. One is for internal energy, and then enthalpy, Helmholtz energy, and the Gibbs energy. So what do these equations mean? How are they derived? How to memorize them? And what are their applications? Let's derive the first equation, also called the fundamental equation. Assume we have a change from initial state to final state through 2 routes. One is reversible, one is non-reversible. They give you the same delta U because U is the state function. According to the first law, internal energy change equals heat plus W. So in the reversible process, we can calculate both. Let's calculate dW and dQ in the reversible process. Now, in general, work is calculated by negative P external times volume change. But for the reversible process, the pressure of outside the pressure always equal to the system pressure. So the work can be calculated by negative PdV instead of external pressure. All right, so that's work. How do you calculate the heat? Now remember, when studying Carnot cycle, we showed that there's a state function relates to the heat of a reversible process divided by temperature, and this is defined as entropy change. All right, so that tells you for a reversible process, the heat is equal to temperature times entropy change. Okay, so this is only valid for reversible process, and therefore the first law applied to the reversible process gives you this equation: du equals TdS minus pdV. TdS represents the heat in the reversible process. Negative pdV represents work in the reversible process. Now, however, this equation applies even for non-reversible process because all these terms are state function. So the interesting thing is we derive this equation from reversible process, but the result only involves the state function, and therefore it applies to any process. Okay. However, if it's not a reversible process, TdS does not represent heat. Negative pdV does not represent work because work is negative external pressure times volume change. But if you combine these two state functions together, you give you internal energy even for non-reversible process. And that's why this equation is called the fundamental equation. It applies to all steps, all processes. Let's compare internal energy with the familiar function distance. In physics, you learned that distance equals speed times time. And therefore, we say distance is a function of time because it changes with time. All right. Now, if speed is not a constant, speed changes with time also, then we can only choose a small time interval, and that distance equals the speed in this time interval times dt. So ds equals vdt. Okay, and the speed tells you how fast the distance change with time. It's per seconds, how many meters. Now let's come back to the equation we just derived. And if we only look at the first term, du equals TdS, compare with ds equal Vdt, and you can see here the internal energy is a function of entropy. Just like here, distance is a function of time. It changes with time. Here, internal energy change with entropy. So what is temperature? Well, just like this equation, the speed, tells you how fast distance change with time. Here, temperature tells you how fast internal energy change with entropy. And so we can write T equals derivative of internal energy with entropy. So it's just like speed is meters per second. Here it tells you how much internal energy change per unit of entropy change. Okay, it tells you how fast internal energy change when entropy change. That's the temperature. Now if we look at the second term, then you can see internal energy is a function of volume. So it changes with volume. And negative pressure then tells you how fast internal energy change with volume. Okay, again, just like speed tells you how fast distance change with time. In the negative pressure tells you how fast internal energy change with volume, and we can also write a derivative of internal energy with volume. So the internal energy change per unit of volume, that's the negative pressure. Okay, so we'll summarize these equations in the next slide. In the last few slides, we derived the fundamental equation for internal energy, du equals TdS minus pdV. And this tells us that internal energy change with entropy and volume. It's a function of entropy and volume. Temperature measures how fast internal energy change with entropy. It is a derivative of internal energy with entropy. Now, because internal energy has two variables, not only entropy but also volume, so the derivative should written as a partial derivative, which means that we keep the second variable volume constant, only change entropy. The derivative of internal energy over entropy is temperature. Similarly, we keep entropy constant, only change volume. The internal energy derivative of volume, the partial derivative, is the negative pressure. Internal energy is a state function. Okay, so the differential in calculus is called exact differential. In calculus, if we have function z is a function of two variables x and y, if z is a state function, then we have equation the second derivative of z over x and then y. So this means your first derivative of x and then y should equals to the function z derivative of y first and then x. Okay, so two second derivatives are the same. Okay, for internal energy, it's also a state function, and therefore the internal energy derivative of entropy and then y should equals to the internal energy derivative of v first and then entropy. Now, note that temperature is already a first derivative of internal energy of entropy. So if temperature derivative of volume, that's the second derivative, the left side, because internal energy derivative of entropy, that's temperature, and then derivative y of volume. This should equals to the negative pressure derivative of entropy, because negative pressure is already the first derivative of internal energy over volume, and then you derivative of entropy. So you have this equation. Temperature, you keep entropy constant. Temperature derivative of volume should equals to negative pressure partial derivative of entropy when volume is constant. And this equation is called Maxwell relation. How do you remember this fundamental equation for internal energy? We derived this equation from a reversible process. So TdS represents the heat involved in the reversible process, and negative pdV represents work. Now this equation tells us that internal energy has two variables, entropy and volume. Okay, and temperature represents how fast internal energy change when entropy change, and negative pressure tells us how fast internal energy change when volume changes. We combined the first law and the second law and derived the fundamental equation for internal energy, du equals TdS minus pdV. Using this equation, we can derive 3 more differentials. So let's try one more. Okay, so we start with enthalpy. The definition of enthalpy equals U plus PV, and therefore the differential of dH should equals to du plus dPV. And because du equals TdS minus pdV, so dH equals TdS minus pdV plus dPV we can write as pdV plus Vdp. So negative pdV, positive pdV cancel each other. We get TdS plus Vdp, and that's the second differential. Similarly, if we start with the definition of Helmholtz energy, Gibbs energy, we can get 2 more differentials. Okay, now the last one, all right, the last one is about the Gibbs energy, and this equation is so important that it is called the fundamental equation of chemical kinetics. Note that all these equations, they have 2 terms. One is about temperature and entropy. So TdS, TdS, negative SdT, negative SdT. And the second term is about the pressure volume. So negative pdV, positive Vdp, negative pdV, positive Vdp. Okay, particularly if we compare the first fundamental equation of internal energy and the fundamental equation of chemical kinetics of Gibbs energy, you can see that everything is opposite. TdS, negative SdT, negative pdV, positive Vdp. So if we know one, we know the other, just opposite the other one. Okay, and that's very important 2 equations. Okay, we're going to talk more about the Gibbs energy equation. How do you remember the fundamental equation for Gibbs energy? We start with internal energy, du equals TdS minus pdV. This equation can be easily derived by applying the first law to a reversible process. So in a reversible process, TdS is the heat, negative pdV is the work. All right, then we opposite each term. TdS becomes negative SdT, negative pdV becomes positive Vdp, and that's the dG. Also, okay, note that in contrast to internal energy, which is a function of entropy and volume, Gibbs energy is a function of temperature and pressure. And these are the 2 most natural variables that can be controlled. Okay, by comparing with the fundamental equation for internal energy, we can easily find out that negative S tells you how fast the Gibbs energy changes with temperature, and the volume tells you how fast Gibbs energy changes with pressure. All right, we'll talk more about this in the next slide. We now have the fundamental equation of chemical thermodynamics. dG equals negative SdT plus Vdp. This equation tells us that the Gibbs energy is a function of temperature and pressure. Negative entropy is the partial derivative of Gibbs energy over temperature when pressure is constant. Similarly, volume is the partial derivative of Gibbs energy over pressure when temperature is constant. Now, just like the case of internal energy differential, we have the second derivative of Gibbs energy over pressure temperature equals the second derivative of temperature and then pressure. Now, because volume is the first derivative of Gibbs energy over pressure, if volume derivative of temperature, that's the second derivative on the left side. And because negative entropy is the first derivative of Gibbs energy over temperature, if entropy derivative of volume or pressure, that's the second derivative on the right side. Okay, and therefore you have one more Maxwell relation. The partial derivative of volume over temperature under constant pressure equals negative entropy partial derivative of pressure over under constant temperature. Now we see each differential, okay, has a associated Maxwell relation, and we'll see summarize 4 of them in the next slide. Here are the 4 exact differentials. We derive the first one, du equals negative TdS minus pdV, by combining the first law and the second law. Using this equation, we can derive 3 more differentials, and the most important is delta G equals negative SdT plus Vdp. This equation can be obtained by opposite the first equation. So TdS becomes negative SdT, negative pdV becomes positive Vdp. And we see that each equation has a Maxwell relation associated with these differentials. One application of these Maxwell relations is that in some cases we cannot measure a derivative directly, but we can measure indirectly using these relations. For example, the change of entropy under constant change of entropy when pressure changes under constant temperature cannot be measured directly. Maxwell relation tells us that we can measure this change by measuring volume change over temperature when pressure is constant. With this fundamental equation of chemical thermodynamics, we are now ready to study the dependence of Gibbs energy on temperature and pressure. So let's first look at the dependence on pressure, assuming temperature is constant. So dt is 0, delta G equals V times dP. Now for solid and liquid, pressure has a little effect on volume. Volume is considered a constant. And if we integrate, so delta G, all right, for measurable pressure change, you integrate Vdp. But V is constant. You can move out of integration and you get V times delta P. Okay, so for solid liquid, the Gibbs energy change due to the pressure change can be simply calculated by volume times pressure change, delta P. Okay, now if it's a gas phase, then volume will change when pressure change. So you cannot simply using this equation. You have to integrate. Okay, we're going to derive equation for the gas phase later. But first, let's look at an example for the solid liquid delta G when pressure change. Calculate the change in molar Gibbs energy of liquid water when the pressure is increased isothermally from 1 bar to 2 bar. So this is about liquid. Okay, it's about liquid Gibbs energy change when pressure change. And the equation we just derived is Vdp, V times delta P. Because it's about molar Gibbs energy, therefore we use molar volume. For water, molar volume is 18 cubic centimeter per mole. All right, remember 18 gram, that's the molar mass of water, and divided by 1 gram per cubic centimeter, that's the density, and that gives you molar volume. Okay, and plug in the equation delta G equals delta V times pressure change. Now pressure is 2 bar minus 1 bar, give you 1 bar, and 1 bar equals 1 times 10 to the 5th power Pascal, and therefore the delta G change is 1.8 joule per mole. So for liquid water, when pressure increase 1 bar, the Gibbs energy increase 1.8 joule. Later we'll see for gas phase water, when the pressure increase same amount 1 bar, the Gibbs energy increase about 1,000 times of this value. Let's now derive equation to calculate the delta G for gas phase. Okay, we just showed in the last slide that delta G can be calculated by integration of volume dP when the pressure change from P1 to P2. All right, so this comes from the fundamental equation of chemical thermodynamics when temperature is constant. All right, if it's gas phase, if gas phase obeys ideal gas law, then pressure, volume, they are related by ideal gas law. So PV equals nRT, then volume is nRT divided by P, and plug in here. All right, we have this equation, nRT over P dP integration. Now, if temperature is constant, all right, so then nRT can all be out of the integration, and the integration of dP over P is ln P, and therefore the delta G can be calculated by nRT ln P2 over P1. So that's the Gibbs energy change when pressure change from P1 to P2. You may notice that there are several equations resembles this delta G equation, and these are reversible work and constant temperature entropy. Both of these equations contain ln V2 over V1, while the Gibbs energy change has ln P2 over P1. Okay, one is due to the volume change, one is due to the pressure change. Now, how are these three equations are related? So Gibbs energy and entropy are related by delta G equals delta H minus TdS. If temperature is constant, delta H is 0, so delta G equals negative TdS. All right, so this needs to times negative nRT. All right, Boyle's law says V2 over V1 equals P1 over P2. All right, if you change negative sign to positive, then ln P1 over P2 becomes ln P2 over P1. All right, and how does these two relation are related? Now, W reversible work for a constant temperature, reversible work equals negative heat. So the entropy is calculated by negative of this W divided by T, and that gives you the entropy equation. A simple question about Gibbs energy change of gas phase. Calculate the change in molar Gibbs energy of water vapor. Treat it as a perfect gas when the pressure increases isothermally from 1 bar to 2 bar at 298 Kelvin. Now, we already calculated liquid water. The Gibbs energy change is about 1.8. So for liquid water, All right, so 1.8 joule per mole. Now for gas phase, we should use equation nRT ln P2 over P1. Okay, so for molar Gibbs energy change, we use RT because n is 1. All right, so RT ln P2 over P1. So plug in the equation, R constant, temperature ln P2 over P1. So what we have is 1.7 kilojoule. Okay, note liquid water is joule, and here is kilojoule, and therefore for gas phase, all right, the entropy of Gibbs energy increase 1,000 times greater than the liquid for the same amount of pressure change. And this is not surprising because the fundamental equation for chemical thermodynamics says dG equals negative SdT plus Vdp, and when temperature is constant, delta G equals Vdp. So that V tells you how fast the Gibbs energy change with pressure. All right, and so when the pressure change is the same, then it depends on volume. And the gas phase, the volume is much greater than the liquid, and therefore Gibbs energy change much faster in gas phase than the liquid phase. To calculate the Gibbs energy change due to the pressure change for the gas phase, we use nRT ln P2 over P1. Delta G is the Gibbs energy change from P1 to P2, and therefore it is G at P2 minus G at P1. All right, that is nRT ln P2 over P1, and we can modify this equation becomes Gibbs energy at P2 equals Gibbs energy at P1 plus nRT ln P2 over P1. Now, molar Gibbs energy at P2 then is molar Gibbs energy at P1 plus RT ln P2 over P1. If we assume P1 is 1 bar, okay, then this Gibbs energy at 1 bar, that's the standard state, okay, molar Gibbs energy, and RT ln P2 over 1 bar. Okay, so the equation is now becomes standard state Gibbs energy plus RT ln P2 over 1 bar, because in this equation we only have one variable P2. P1 is a constant 1 bar, and therefore we don't need to use P2. We can use just P, and now we have this equation. The Gibbs energy, molar Gibbs energy at a certain pressure equals standard state molar Gibbs energy, that's 1 bar, okay, Gibbs energy, plus RT ln P over 1 bar, okay, standard state. P naught means one standard state, that's 1 bar. Now you may ask why we keep it, because it's just 1. Anything divided by 1 is just P. The reason is for the unit. All right, if we don't have P naught, just ln P, then the unit is bar. But if we divide by P naught, then that means this has no unit. It's a unitless, the natural log. Okay, so this is for unit purpose. So we have to keep it there, just 1 bar. All right, and this is a very important equation. So it tells you that at any pressure, the Gibbs energy can be referenced to the standard state Gibbs energy, but it's not a standard state, so you need to add correction due to the pressure, that is RT ln P over 1 bar standard state. We just showed that for an ideal gas, the molar Gibbs energy at any pressure equals the molar Gibbs energy at the standard state plus a pressure correction term, which is RT ln P over 1 bar. This equation is applied for ideal gas. Okay, what if it's not ideal gas? Now for non-ideal gas, we still keep the same format. So molar Gibbs energy at a certain pressure equals standard state molar Gibbs energy. But now the pressure is replaced by a term called fugacity. So ln fugacity divided by 1 bar. Fugacity is the ideal gas pressure you would need to obtain the correct value of molar Gibbs energy at the real pressure P. So we want to keep the form. So we need a fugacity that can give you the correct molar Gibbs energy using the same format equation. And this can be considered as effective pressure that makes the above equation exactly true. In the last few slides, we studied how Gibbs energy changes with pressure. So now we are going to study how Gibbs energy changes with temperature. According to the fundamental equation, dG equals negative SdT plus Vdp. All right. So the first one tells you how Gibbs energy changes with temperature. The second one tells you how Gibbs energy changes with pressure. When pressure is constant, then you have dG equals negative SdT, and the negative entropy tells you how fast the Gibbs energy changes with temperature. So negative entropy is the partial derivative of Gibbs energy over temperature when pressure is constant. Okay, so this already tells you how Gibbs energy changes with temperature under constant pressure. But the later chapters shows that equilibrium constant is related to Gibbs energy by delta G equals negative RT ln K. That tells you equilibrium constant ln K is related to negative delta G over RT. So it's a function of G over T, not Gibbs energy itself. It's the function Gibbs energy over temperature. So here we are going to derive equation that tells us how G over T changes with temperature. Because G over T is related to equilibrium constant, okay, not Gibbs energy itself. So how do we do that? We look at the derivative of Gibbs energy over temperature, derivative over temperature. All right. Now in calculus, if we have a product U times V derivative, then we first derivative U and then times V plus U times V derivative. Now G over T we can think about as G times 1 over T. So this derivative will be G derivative times 1 over T plus G times 1 over T derivative. And 1 over T derivative is negative 1 over T squared. And therefore, this derivative is 1 over T times partial derivative G over T, all right, plus negative G over T squared. Okay, so what is the partial derivative of G over T? Okay, this is here. The Gibbs energy change with temperature under constant pressure is negative entropy. And so here gives you this equation, the negative entropy over T minus G over T squared. Now to combine these two equations together, we need to times T so that they all have T squared. All right, so times T, here also times T. So we have this equation, negative TS plus G over T squared. Remember, G is H minus TS. And therefore, TS minus TS cancel each other. So we finally have this equation called Gibbs-Helmholtz equation. The function G over T derivative over T under constant pressure is negative H over T squared. Okay, so if we want to know equilibrium constant change with temperature, then this will be delta G. Okay, the reaction Gibbs energy over T, and then the right side will be delta H, reaction enthalpy. Okay, so this tells you that the sign of delta H will determine how equilibrium or Gibbs energy change with temperature. All right, so and whether the delta H is positive or negative, or whether the reaction is endothermic, exothermic, give you opposite sign. So then the equilibrium constant may increase or decrease, all right, with temperature, depends on the sign of delta H, or whether the reaction is endothermic or exothermic. So we're going to study this in the last chapter. In summary, in this chapter, we have derived several differentials, and one of the most important is delta G equals negative SdT plus Vdp. And this equation tells us how Gibbs energy change with the temperature and how Gibbs energy change with the pressure. And we showed that for solid liquid, when pressure changes, the Gibbs energy change can simply by multiply volume times pressure change. Okay, for gas phase, the delta G equals nRT times ln P2 over P1. All right, so if P1 is assumed to be standard state, then we can modify this equation and becomes Gibbs energy for a gas at any pressure can be referenced to the standard state plus RT ln P over 1 bar. And this equation is very important. We're going to use this for all the rest chapters. Okay, and if it's not ideal gas, then the Gibbs energy can still reference to standard state plus RT ln fugacity divided by 1 bar. All right, now for temperature dependence, we derived Gibbs-Helmholtz equation that tells you how Gibbs energy over temperature function derivative over temperature, which equals negative H over T squared. And this will be related to equilibrium constant change with temperature. And we are going to use this in the last chapter. So far, we derived the fundamental equation assuming number of moles does not change. In fact, Gibbs energy is extensive property, means that when you change the number of moles, Gibbs energy also change. And therefore, we need to add one more term and tells you how Gibbs energy change when number of moles change. And the GM is the molar Gibbs energy. So when you change the number of moles, Gibbs energy also change by molar Gibbs energy times number of moles change. So molar Gibbs energy can be written as the derivative of Gibbs energy over number of moles when pressure, temperature are constant. Now, molar Gibbs energy becomes an important concept that is so important we have a name called chemical potential. All right, so now the fundamental equation becomes dG equals negative SdT plus Vdp plus mu dm. Mu is the chemical potential or molar Gibbs energy. To see how important chemical potential is, let's imagine there's a chemical reaction. The reaction can take place under constant temperature, constant pressure, and that means that temperature does not affect the Gibbs energy change. Pressure does not affect the Gibbs energy change because both are constant, and therefore the only change is number of moles. Okay, reactants decrease with time, product increase with time. So it's the number of moles of reactants product change that changes Gibbs energy, and this change is determined by the chemical potential. All right, so when the chemical reaction takes place, constant temperature, pressure, all right, so the Gibbs energy change is determined by chemical potential. And another example is the phase transition, also constant temperature, constant pressure. again, it's the chemical potential determines the Gibbs energy change, and therefore we'll see how important chemical potential is determining the Gibbs energy change for phase transition for chemical reactions. Now we learned that molar Gibbs energy can be written as the standard state molar Gibbs energy plus RT ln P over 1 bar. Molar Gibbs energy is chemical potential, and therefore we can write the chemical potential is standard state chemical potential plus RT ln P over P naught. And you are going to see this equation again and again in the next few chapters.